Great. Excellent. Well, I'd just like to thank the organisers, so Sergey, Filipov, for inviting me to talk today. It's a real pleasure to be able to be involved in this conference. And I'm just going to present some of the work that I've done since moving to Loughborough, and I've been here now for about 8 years. So first of all, my slides will move. That's it. First of all, if you're not sure where Loughborough is, it's a strange university right in the centre of the UK. Not many people know where it is, so it's around about here on a map. And Loughborough is very strong in engineering and also in sport. So you may have heard of Loughborough University through the kind of sporting prowess that it has. And an interesting fact about Loughborough is if it was a country, it would have finished 6th in the overall medal tables of the 2022 Commonwealth Games. So this is quite unique for Loughborough. And if you're ever in the UK and you wish to visit, please do let me know. We'll be more than happy to have you come and visit. So as I said, I'm going to be talking today about some of the work that I've done here at Loughborough. And my expertise are kind of as a synthetic polymer chemist, and I'm mainly talking about synthesizing, characterizing and using polymers all the way through from linear polymers on the left hand side, if I just get my pointer up, all the way through to kind of polymer particles such as the ones shown on the right hand side here. And we make these materials using lots of different techniques. We're typically using controlled polymerization or reversible deactivation polymerizations such as raft. I've had an interest in making dendritic materials based on the work that I did during my PhD, and this is using some organic chemistry. And then we use some kind of self-assembly methods and emulsion dispersion polymerizations to make these larger particles. So we can make things all the way from kind of a few nanometers in diameter all the way up to hundreds of nanometers or even microns in diameter. And this is quite a broad range of materials to make, but importantly, the characterization techniques that are used to analyze these types of materials are very similar throughout. So we can make these materials and analyze them using NMR, size exclusion, thermal analysis, light scattering, surface tensiometry, and microscopy. And I'm going to show you some of that data as we go through today. But I'm particularly interested in responsive polymer particles. And we typically, as I say, make these using a reversible deactivation polymerization technique known as raft. And I don't think anybody else has introduced raft today, so I'm just going to use one slide to do that. And raft polymerization is an interesting process. It's a type of free radical polymerization in which we use our typical monomers that we would use for free radical polymerization, so activated carbon-carbon double bonds. And we also add in what's called a CTA, or a chain transfer agent. And this is a thiocarbonyl thio group that has this R and Z groups on, that allows us to control and mediate this polymerization. And what happens during this polymerization is we get insertion of monomers into this labile RS bond here, and the growing polymer chain will be here, and this end group, the chain transfer agent, will reversibly come off and come on this polymerization. It will reversibly cap the propagating chain, and it will therefore control and mediate that polymerization. It's also a useful handle for things like UV quantification for further reaction. We can do things after the fact as well. But importantly for this, we get a controlled molecular weight, a predefined molecular weight. We get a narrow dispersity of polymers, so all of our polymers are around about the same length. And it's really tolerant to quite a wide range of monomers and conditions. So it's a very easy and interesting type of polymerization to use, and very commonly used in the literature, I would say. So why are raft polymers useful? And I've drawn it as this kind of chain. Our red group here is just our repeating unit, and our yellow group here is the raft end group. So they're useful for lots of different reasons, and we typically use them to make controlled architectures, so controlled branched polymers, for example. We can do things like chain extension to make amphiphilic block copolymers. We can modify the end groups to insert things like fluorescent groups. We've done quite a lot of this work. And we can also use them to make these larger particles that I was talking about earlier in raft emulsion or raft dispersion type polymerization. So they're really interesting. It's a really interesting technique, very simple to do. And if you can do a free radical polymerization, essentially you can do a raft polymerization as well. So this work started quite a number of years ago with a very talented PhD student, Dr. Anne Mabir, who worked in Professor Rachel O'Reilly's group when I was there at the University of Warwick. And I was working with Anne on some some projects that were related to what I was doing in industry at the time, and we were trying to fluorescently label the polymers that we were making, and we realized that some of the fluorescent labeling wasn't working very well for our materials, so we designed this project based around that. And what this is looking at is essentially a pH responsive polymer. So I said I'm particularly interested in stimuli responsive polymers, both temperature and pH. We've done quite a lot of work with. And this particular polymer, dimer, may be recognized by some people in the audience, is a tertiary amine containing polymer that when it's protonated, as shown on the right hand side here, becomes completely hydrophilic, so swells in water or dissolves in water. And that's because of in this case, we've dissolved CO2 into the water. We've got carbonic acid, and this material becomes protonated. When this material is deprotonated, it becomes completely hydrophobic. So this gives us a nice kind of environment in which we can probe what that fluorescent material is doing. And so the way that we do this purge, we simply take our material, you can see the code name here, but simply take our material and we put a needle in with a pressurized CO2 cylinder, and we literally bubble CO2 through this solution. And the reason why we used a bubbling of CO2 rather than the addition of kind of hydrochloric acid or sodium hydroxide to change the pH is that we didn't want to change the concentration of our solution at all, because our fluorescent materials is quite sensitive to concentration. So by just doing a purge, by just dissolving CO2 in this system and then removing the CO2, we're keeping the same concentration and we're not adding salts or anything to our material, which may cause our particles to come crashing out. So that's why we did that. So what were our particles like? They were made from a PEG shell, so polyethylene glycol or oligoethylene glycol. This is hydrophilic. We've got our red monomer, which is hydrophobic, which can switch. We've got a cross-linker, which holds everything together. And in this case, it's not too important, but we've got our fluorescent monomer. And this thing was the thing that we found was responsive to the environment in which it was in. So we did a kind of emulsion polymerization, and we made these fluorescently labeled particles in which the fluorescent group was within the core of the particle. So we can image these using things like TEM. The scale bar here is 100 nanometers. These are spherical. They're all around about the same size. And what they look like in solution is quite a milky looking solution. These things are quite concentrated in this solution. And under the UV light, we can see that these have a fluorescent response. These are giving out some emission. So what we did then is we bubbled this with CO2. So now we've got this swollen particle where the fluorescent tag is in the core of the particle. And now we can see that this thing is completely switched off. The fluorescence is completely gone. So our fluorescence emission spectra here, before we do the swelling, we can see we have this nice emission at about 500 nanometers. After we do the swelling, that's almost completely switched off. And we've got light scattering data here. So before we do the swelling, our particle is smaller. After we do the swelling, it's completely shifted to a much larger particle size. And so this was really neat because we were able to do this over multiple cycles. We were able to kind of bubble with CO2 and then bubble with nitrogen to remove the CO2. And we were able to do this over and over again, getting an increase and decrease in the size here, and also a switch on and switch off of the fluorescence as shown in this graph on the right-hand side. And we can see this in this hopefully quite nice video here, which has been sped up by 60 times. The time of the reaction is about 10 minutes, but we're just putting this under a UV light and seeing that over the time of the bubbling of the solution, the changing of that pH, our fluorescence is completely switched off. So we get this nice responsive nature of our fluorescent material that's encapsulated in the core of that particle. And this was the basis really for a lot of the work that I started to think about while I was at Warwick, but actually I started to do in earnest since I moved to Loughborough. And this was something that I'd wanted to do based on magnetic resonance imaging. So what is magnetic resonance imaging, or MRI? So anybody who's had an MRI or seen an MRI image may recognize the kind of image shown on the right here. So MRI is a medical imaging technique that allows clinicians to visualize soft tissue within the body. And this is what an MRI kind of scanner looks like. Again, I've just stopped my pointer. And it's essentially an NMR machine that a person can fit inside. We don't call it nuclear magnetic resonance because people don't like to get into an instrument that mentions anything to do with nuclear because they think it's slightly concerning. So MRI is looking at the proton NMR basically of the signals of the soft tissues, so water containing tissues and fat containing tissues within the body. And these are the MRI scan that's obtained is a map of that proton density. The advantages of this are that there are no radiation or side effects that you would get with a CT scan or an X-ray. You can get excellent spatial resolution, and it's multiplanar. You can do this in 3D. There are obvious disadvantages. It's quite a costly procedure, and it's quite lengthy too. But what advantages are there? We can start to image things really, really clearly, particularly if we add in something known as a contrast agent. So the images shown on the left-hand side here are the MRI image of a brain before and after we've added this contrast agent. And this is allowing us to directly visualize and easily visualize this tumor here. And what kind of contrast agents are used? So these are typically, some of the commercially available ones are Magnavist and Dotarim. And these are basically gadolinium complexes, gadolinium ligand complexes that are mostly based on gadolinium. They're T1 contrast agents, which are brightening, and they're predominantly administered by intravenous injection. But if you know anything about the kind of heavy metals in the center of the periodic table, you'll know that these are problematic in that if we start to ingest these materials and if they start to bind to the ligands that are available within our body, these things are cumulative and we can cause problems with heavy metal poisoning. So it's really important that these ligands are very stable and that they're able to be excreted by the body. So how can we start to change the contrast of these imaging agents then? So if we take our gadolinium complex and we think about our ligand, then what happens when that thing goes into solution is we get this kind of inner sphere and outer sphere of water. And we can affect the contrast or the MRI image, so in the same way that we can affect the NMR of these materials by thinking about changing Q, which is the number of bound water molecules, the water residence time, that the water within the inner sphere and the outer sphere, how they're exchanging. More easily for us as a polymer chemist, we can start to change the rotational tumbling time. And how we do that, or what that does, is if we think about our gadolinium and we think about our NMR of any proton system, then basically what we're doing is we're looking at the relaxation after the alignment of these protons in a magnetic field. So we're doing exactly the same here. And if we imagine our gadolinium complex is tumbling very quickly because it's a discrete complex, if we now attach this to a macromolecule or a polymer, we can affect the tumbling of that system, and we can therefore give these materials a higher relaxivity. We've got other advantages of attaching these things to polymers as well. So we can get things like a longer biocirculation time, so over 2 hours. So often you'd have to have an injection of this contrast agent immediately before your image was taken, and if there was a problem with the machine or a delay in your appointment time, you might have to be re-injected with more material, which is not ideal. You've also got the possibility for targeting, and you can decrease the amount of gadolinium that's needed to be injected, which is actually quite a huge dose at the moment. So we're not the first people to think about this, but there have been other groups who've done this, and this is quite a nice example from 2012. And in this example, PEG polymer was, or PEG monomer, sorry, was co-polymerized with this activated monomer here, which allowed reaction of this contrast agent. So they did the polymer synthesis, they functionalized it, they deprotected it to allow these acid groups to bind to the gadolinium. They then complexed it, and then they ended up with this resulting polymer shown at the end here. But there are multiple steps associated with this, and at each point you have to do purification, and you have to do check that you've got these materials as you expect. And also the other problem that we have is if we have a gadolinium containing material, it's very difficult to get an NMR spectra of this because these gadolinium will impact the NMR by their very nature. So we wondered if we could make this a little bit simpler and start to think about direct polymerization. So then we started work with Tom Berkey. So this is work done with myself and Dr. Stephen Butler here at Loughborough University. Tom was a shared PhD student who really grasped the organic synthesis required and also the polymer synthesis, and did an excellent job of that. Started this project off very well. So what Tom was able to do was to design some gadolinium containing polymerizable materials. So these now have a methacrylamide group which allows us to insert them into a polymer. And we designed different ligands, one which just had one functional group, one with two. We had two, both cis and trans across the molecule, and we also had a short and a long linker. So we designed all of these, and we started to polymerize them into to make some polymers. And what we found was that basically, as we took our gadolinium monomer and we looked at the relaxivity of that on its own, it was very similar to that of gadolinium DOTA. However, when we started to polymerize this and make it into a linear polymer, we can see that we increase the relaxivity of that material. And when we polymerize it into a hyperbranch polymer, we were able to increase it even further. So we were able to eventually get between a 5 to 8-fold increase in the relaxivity compared to our gadolinium DOTA. And we found that, as expected, actually, our cis orientation short arms gives the highest relaxivity because this is the most rigid structure that we formed. And as I say, this is kind of simplifying Tom's 3 or 4 years of work down to a couple of slides, but I'm not going to go into the detail of how we did that. We can see that in the paper or ask me a question. What we were also able to do is show that this worked with multiple different polymers. So we did this mainly with this monomer here because it was biocompatible, it was water soluble, but it was also able to be analyzed along with our organic GPC system. So it was well chosen monomer, but we did a number of other monomers, and we showed just by the BMS shift, which shows that there's been the incorporation of this gadolinium group, that we were able to incorporate this gadolinium into all of these different types of polymers while still maintaining a good control over the dispersity and still maintaining a good control over the polymerization itself. So that paved the way really for our second PhD student, and this is Katie, who's working in the group just finishing up now. And what we started to do with Katie's project is think about not just MRI agents and how we can control those, but could we also start to think about some dual imaging agents? And for this, we wanted to include both a gadolinium complex and an optically active terbium complex. So the first stage of Katie's project was to synthesize these polymerizable complexes and then to start thinking about particle synthesis with the controlled positioning of these imaging agents in the core and in the shell. And we can control that by using our raft polymerization and doing a chain extension reaction, as we showed before. So by thinking about that the shell has a better water access than the core, we can start to place these materials in the shell and the core. But actually, we've seen some quite different results to what we're expecting. I'm not going to talk through all those here today. This is unpublished work, but that paper will hopefully be coming out soon. And what Katie has designed are these complexes, making sure that we have the same kind of ligand system, and we can just switch out the metal to switch between an MRI and an optical imaging agent. And that took some quite clever design of these systems. So in both of these, we obviously need our polymerizable group. That's important. The things that are important in MRI are our bound water molecule, as we said before. So we need to make sure we've got this bound water molecule, and we also need to make sure that we've got the stability of this gadolinium complex by the binding of these acid groups to this, as well as this pyridine group here. But within our optical imaging agent, it's really important that we have this antenna molecule. So this group here had two jobs in this system, but we found that we were able to successfully form both gadolinium and terbium complexes, and this one is MRI active and this one is optically active. So that was nice. And what Katie then started to focus on was tuning the particle size so that we could optimize this for the MRI and the optical imaging agents. And she was able to show that by taking a simple system, again, raft polymerization of polyethylene glycol monomer containing monomer methacrylate group now, and chain extending it with a methyl methacrylate, we were able to vary the core size of these particles, and we were able to get particles all the way down from about 25 nanometers all the way up to around 300 nanometers. We could go higher, but these, as mentioned before by Sergey, do start to become unstable and settle out of solution. So we can get nice, stable, well-defined particles in a large size range just by changing the variation of the core size there. And that was really nice. And we showed that this was able to be imaged both by AFM and also measured by DLS and light scattering. And this was quite neat. And Katie also noticed some quite subtle differences in the changing of the shell of these monomers, which hadn't really been shown before in the literature. So overall, what did Katie find based on her systems and Tom's systems, is that if we started to think about varying not only the architecture of these polymers, we talked before about the fact that we can improve the relaxivity if we incorporate this into a branched polymer, but now if we start to think about taking our gadolinium complex with a linear polymer, a brush-like polymer, and then a particle polymer, we can see that we get the best relaxivity with this particle system. And that's because this the tumbling of this system is significantly reduced, because this is now attached to a much bigger macromolecule. And we can tune this a little bit further, as we showed before with Tom's materials. And what we're looking at in the future is seeing if we can incorporate some kind of relaxivity, as we did with our fluorescent monomers in the beginning. So this is kind of ongoing work. And just switching tack a little bit for the next couple of minutes, I'm starting to think about some different responsive systems. And this was a collaboration that came as a result of a RAPS conference here in Loughborough. And this is with Richard Darcy, who's now based in the US. But Richard works has worked quite a long time on these redox responsive polymers. So these kind of polysulfide materials. And what Richard had been able to show is that he'd been able to make these particles of this cross-linked polysulfide material, been able to make some nanoparticles in a similar kind of size ranges we'd been already talking about. So we started to work with Richard to see if we could utilize these materials in some other kind of processing techniques that we're able to do here in the department. So this is some work done by Charlie, who's a PhD student who's now at the University of Leeds. And Charlie's project was based around the electrospinning of some natural materials, which I'll show in a second, and also these polysulfide materials. So what we'd already shown is that we could encapsulate particles into electrospun fibers just by incorporating them into the solution that was being electrospun. And this worked much better than we expected, actually. And what Charlie did was took these polysulfides that have been synthesized by Richard, and these materials are interesting because they're able to be degraded by things like reactive oxygen species, which are often present in diseased tissue. So Richard was really interested in what these materials did before and after electrospinning, and what we were looking at is how did it impact the electrospinning process. So electrospinning is a way of making well-defined nanofibers of material, essentially by taking a solution of some polymer, and if the polymer is high enough molecular weight and can entangle well enough, then what happens as you electrospin this is you extrude it out of a syringe, you apply a voltage difference between the syringe and the collecting plate, and as that material comes out of the syringe, basically makes a Taylor cone, the polymer dries and the dry fibers are collected on the collecting plate. This is a lot more complicated than that, but that's essentially what you do. And what we were able to do is incorporate these particles into the fibers and look at how it impacted the fiber materials themselves, and also whether we could then use these for their intended purpose of the redox reaction that they were made for. So what Charlie was able to show that the electrospun fibers with no particles in there were quite well defined. As we started to increase the weight percent from 2 to 4 to 14.3, so sounds a random number, that was the highest volume we could get in there, we can see that we get a slight increase in the particle diameter. And so as we increase the particle concentration, it increases the fiber diameter. And we can start to see the inclusion, even when the particle size is bigger than the fiber diameter, we can see that we do get encapsulation of these, and we can see a bulge in the fibers themselves. But importantly, the polypropylene sulfide nanoparticles did retain their antioxidant or anti-inflammatory nature after the electrospin, and this was proven by the comparison of the properties before and after. So this is really important, that these particles weren't destroyed by the electrospinning process. And by incorporating these things into electrospun fibers, you can start to imagine that you can start to make things like wound dressings and flexible materials, rather than just have things in solution, which is very interesting. So what Charlie's then able to do, and this is so far unpublished, hopefully soon to be published, is to show that we could directly electrospin polypropylene sulfide without making particles, so just taking the linear polymer now, by combining it with a small amount, or a large amount of some PCl, which is quite well defined and easy to electrospin. The problem with these polypropylene sulfides is that they weren't really able to be high enough molecular weight to give us the entanglement needed for electrospinning. But by combining these, we were able to do this very easily. And as I say, Charlie's project was also based around the electrospinning of some natural materials. So lastly, just for the last kind of couple of minutes, I just want to talk about one project that I'm really excited about, that we've got some funding for a number of PhDs to start in October for. And this is based, again, with Dr. Stephen Butler in the chemistry department, looking now at encapsulating ion sensing molecules into materials. So I am a chemist by training, but after moving to a materials department, a materials engineering department, I realized that really we wanted to start to move towards making materials and using materials rather than doing everything in solution. Materials engineers are very hands-on and want to see this a lot more. And what this project is based around is the use of ion sensing fluorophores. So these are fluorophores molecules that in solution can bind to some kind of analyte, and when they bind to the analyte, they will give out a specific spectral response based on an emission and a fluorescence. So these are typically based on europium complexes. So these are now drawn slightly differently, but they have a similar structure to those that we've just been talking about. So these are metal complexes with some kind of ligand system around, in which they have a cavity in which whatever the ion that is being sensed can bind to that complex and allow that to have this specific spectral response. So the example shown here is a europium-based sensor that can detect bicarbonate in aqueous solution at physiological pH. So this works in collaboration with some companies who are really interested in seeing if we can make these solution-based sensors into something more materials-based. And very simply, what we've been able to do is now not using a covalent method of linking, just by using an encapsulation of these materials in the core of a hydrophobic core particle. What we've been able to do is use a dual encapsulation technology. So we take our fluorescent molecule, our ion sensing molecule, we trap it in the core of a small hydrophobic cored particle. We then trap those particles in the same way that the previous speaker was just talking about. We trap those particles within a hydrogel, and that hydrogel material is used as a sensing material. So that hydrogel can now do exactly what that solution-based sensor was doing, but it can do it in the bulk rather than in solution. And these are good because they're easy to prepare. We don't get any leaching. So if you just trap directly the small molecule in the hydrogel, it leaches out very quickly. These things are flexible. We can get reversible sensing, and they're tunable based on particle size, based on lots of other parameters that we're looking at changing. And how do they work? So basically, we take our ion sensing molecule in the core of the particle, we add whatever it is we're trying to sense, and that thing binds to our material and gives out our spectral response. And our particles are exactly what we've just been talking about. We can design them to have a well-defined structure and size. They have this hydrophobic cross-linked core, and they have a long hydrophilic shell, which allows us to entangle with that hydrogel material. And we're just talking about SEM images. So we've seen some nice SEM images of the hydrogel without particles. And when we look at the hydrogel with particles, apologies for the fact that the scale bar seems to have popped off these images, but these particles are around about 100 nanometers. So the pore size here is maybe 500 nanometers, but you can see that the particles are filling up those pores in that hydrogel material. And over time, we don't get any leaching of these materials. So we think that this is a really interesting and very simple way of making ion sensing materials that can be used for lots of different applications. And we're looking to exploit that with water companies and with biomedical companies as well. So that leads me just to the kind of summary. So hopefully I've shown you that we're interested in making responsive particles or polymer particles for lots of different applications, particularly for this kind of switch on, switch off of fluorescence and MRI. We've been able to show that we can control particle size just by changing the degree of polymerization. We can control the contrast of our contrast agents by changing whether we make them linear or branched or particle-like. And we've been also able to show that we've got this nice dual encapsulation technology that we're looking to exploit. So just as the acknowledgement There's lots of people I'd like to acknowledge, but particularly here we've got Tom, Katie and Charlie, who did the work in Loughborough, and Anne, who did the work with the fluorescent materials. This is some of the group and some of the larger polymer group, a couple of photos there. And I'd like to thank you for your attention and these people for funding.